In 2007, an American professional runner suddenly collapsed during a marathon and died. He was just 28 years old. In 2018, a Belgian professional cyclist also suddenly collapsed and died. He was just 23 years old. These two tragic cases dramatically demonstrate the impact of the biggest killer in our time, the cardiovascular disease. In fact, heart attacks and strokes are ranked as number 1 and 2 under the world-leading causes of death, even higher as any cancer. And as you can imagine, it's really difficult to diagnose such cases, as I mentioned, because these young people are obviously healthy, so they will not come and see a doctor. And for that, it's really challenging to find their risk. You would also agree that it's not realistic to screen the whole healthy population with any of other existing imaging technology at the hospitals to find such cases. So there should be a better way, right? One possible solution would be to go a step back and to try to understand the progression of such a disease. So to learn why the people are dying of that disease. One option would be from the molecular medicine, trying to identify the potential factors influencing this disease. And on the other hand, there is the biomedical computing, which actually takes these identified factors and trying to predict in computational models, in simulations, how the disease will progress. But how do we know that all these predictions and simulations, how do we know that they are correct? We need to prove them somehow. One option would be to have a very powerful tool which will be able to visualize small pathological changes within the human vessel. Let us have a look in the existing imaging technology we know from our hospitals or from laboratories, what they can do in terms of visualizing changes in vessels. If we look what is existing, one very broadly used method is the so-called magnetic resonance imaging. This is a method which can be used on a full patient, living patient of course, or just a part of the body, and providing you very high contrast images of soft tissue, especially the vascular system, but the resolution, meaning the amount of details that you can resolve within this structure, is very limited with this method. Another standardly used technique in the clinics to visualize the vascular system is the so-called optical coherence tomography. This is a modality which is based on a catheter which is inserted into the living patient's vessels, visualizing the details of the vascular structure from inside, giving amazing, good, highly resolved images. But of course, it is very invasive and by that risky for the patient. The gold standard to identify pathological changes is, of course, the histopathology. This is a modality which is based on taking the pathological tissue, embed it in paraffin, cut it in thin slices, and look at it under the microscope. This modality can visualize even individual cells and can identify pathologic cells in the tissue. But it's very destructive and time-consuming. So what we would look for is a method which is non-destructive, non-invasive, and providing you with high resolution. One potential candidate is the so-called X-ray computed tomography. This is a modality which is also constantly used at the clinics. But if we look what is its ability to visualize pathological changes in human vessels, we will find that it has It produces images with high resolution, but the contrast for the soft tissue is very limited. Now, what if we would take this powerful method and enhance it such that we really switch on the contrast for soft tissue? And this is what I have been working on since more than 10 years now. Let me explain you what I mean by switching on contrast. And let me do this on the example of visible light, as we are all more familiar with visible light than with X-rays. We all know X-rays, we all know that when we talk about X-rays, all started with Mr. Röntgen. And Mr. Röntgen, in 1895, actually, discovered a new kind of radiation, which he called X-rays. They had astonishing properties. They could go through matter and could visualize the inside of the object. And this, actually, from that point on, X-rays became indispensable in medical imaging, but also in the industrial imaging, because of this astonishing property. And from that on, machines improved over decades, that you know from the dentist, for example, or the highly efficient, very fast X-ray tomography systems at the hospitals, or the very fast scanning systems at the security, scanning our luggage at the airports. So all these machines actually improved over decades, became more efficient and better, but the only fact that has not changed since Mr. Röntgen's time is the way how they generate contrast. This is still the same. If we look from the visible light point of view for that, we know when we shine light on an object, its intensity will be diminished depending on the thickness of the object. And this effect we call attenuation. But what we also know from visible light is, if we shine light on an object that looks like a lens, then the light will change its direction. It will be focused to one small spot. And this effect we call refraction. We all know, maybe, or hopefully you know, if you shine visible light on a prism, you will see that it will change its direction and will be even split in different colors. So this is a well-known effect from visible light. Today we know X-rays are the same than light, but in a different energy range. They can go through thicker objects, let's say. But the same effects should happen, so the attenuation and the refraction. What we also know from visible light is if we take the attenuation, the contrast, and try to look at cells under the microscope with this contrast, we will only get a very weak contrast. But if we switch on the different optics into the microscope and look at the refraction of the same cell, we really gain a lot of more contrast. And exactly that, using the refraction as a contrast mechanism to visualize structures, is called phase contrast imaging. We know that with X-rays, these effects also happen, but they are so much smaller. It is much harder to measure them, because these changes, slightly changes as a refraction, are much smaller than in visible light regime. Starting from 1960s, there have been different methods developed to detect these tiny changes in X-rays. And all these methods came from large-scale facilities, so-called synchrotron sources. These are basically very large and bright X-ray microscopes. With large, I mean they have diameters which are ranging from 300 meters to 1 kilometer. And there are only few of them existing worldwide. So, as I told you, there are existing methods measuring the refraction of X-rays. Let's take a patient, in our case a small patient, a mouse, and try to visualize the inner organs of this mouse going to one of these synchrotrons. And what we would expect to get from the conventional, the attenuation contrast, is, as I mentioned already, a high resolution, very high amount of details in the image, but the low contrast for the inner organs of the mouse. But if we take the refraction, so the phase contrast, we gain a lot of more contrast for the inner organs of the mouse. Now let's come back to our previous problem. We wanted to visualize pathological changes inside a human vessel. So we take a human vessel and go to one of these synchrotrons and perform a phase contrast tomography on it. And what we see and what we get is actually an amazingly good image on many, many details. So we even can resolve and detect small, tiny arteries which are supporting the larger artery with blood. So by looking at these images, you would wonder, why should we do any research in that direction at all? Obviously, our problem is solved, so we can study the diseases by going to the synchrotrons. Now comes the downside of these laboratories. Their accessibility. This is very, very low. As a scientist, you have twice a year the chance to apply to get time at one of these experiments, and then to perform some unique measurements. And if you imagine you have your interdisciplinary team trying to test different parameters and to prove your simulations on varying parameters, it's not realistic to do this twice a year in unique measurements. So we need something different, something more efficient, which works in our labs. When I was working on my PhD at such a synchrotron source, I learned that there is a team around a Swiss scientist, Professor Franz Pfeiffer, who succeeded to transfer one of these phase contrast methods to the standard laboratory equipment from the synchrotron sources. So using a standard X-ray source that you know from the hospital or from the lab, and a standard detector which you can commercially buy. And this is where my idea was born. I thought, how cool it would be if you could build an instrument which makes these large synchrotron sources unnecessary for such studies as I told about. And what if this instrument will fit in any small hutch, maximum 3 meters long? And if it would use standardly available, commercially available equipment, and even better, it would produce as accurate images as you can expect to get from the synchrotron sources. My team and me actually built an instrument on an optical table using a standard X-ray source, which you can commercially buy, a detector, and the only thing which we added are the golden structures. These are the optical structures we call gratings, which help us to resolve this refraction of the X-rays, to make them visible. And when we started taking images of mice to compare to what we got at the synchrotron, we had to admit that it is not as easy. We had a lot of problems with our first images, instabilities, different kinds of unwanted features in the image, really bad images. And over years, we learned where these effects, unwanted features come from, and how to correct for them, getting much homogeneous, more homogeneous images without these disturbing features. And up to now, we got outstandingly good at it. What we get now with our instrument in our lab, on 2 meters table, let's say, are the same accuracy as you can expect from such a synchrotron source, the bright X-ray microscope. The only difference is the slightly lower resolution that we have in our setup. But if we just go to the problem, as I discussed, that we have, is to look into pathological changes in the human vessel, and we scan the human vessel in our laboratory, first with a conventional attenuation-based X-ray tomography, getting, again, a high resolution but low contrast, and do the same in phase contrast by getting much higher contrast, actually, within the vessel wall itself. So we will be able to visualize with absolutely sufficient resolution and contrast the pathological changes in our lab. We are just at the beginning, because we now demonstrated that it's feasible in the lab. And my team and me, we are now really excited what will happen if we actually distribute this method to different laboratories, as many as possible, or hospitals. Now I shared a lot of academic research with you, but the question would be, how can we save lives as those I mentioned in the beginning with this idea? And the point is, the more interdisciplinary teams are getting access to such a powerful tool, the more we will learn about the disease, the more we will understand its progression, and hopefully recognize or identify some patterns, in like typical patterns, how it progresses in, let it be even female or male, or special kind of lifestyle, or special kind of children's diseases which these people had. And by that enable any kind of a family doctor to really identify the individual risk of the person and to warn them before they get in trouble. Thank you very much.